Hi to everyone. I'm really happy today to present you a new tutorial, and this tutorial is the results of the question of many users that asked me to simulate the crash of the team. I want to answer to some students that need to do this simulation using Abaqus student version. So in this simulation I will try to use lesser element as possible and to achieve a good solution, a reasonable solution for them, but also to introduce to other users some feature that they have to know to do their simulation. Okay, in this case we have to simulate something like this. I show you just the results to let you know where we want to arrive. We have a team and we want to simulate the crash of the team, something like this. And some of the users have to just do this, others have to determine the minimum load necessary to do this, and others have to design a crash machine. First of all, we need the minimum load, or well, not the minimum, but the load that is necessary to cause the instability and to crash our team. Well, the answer is linked to a very simple solution, the buckle load. Why I always talk about the buckle load? I'm not a really expert of crashing teams or industrial equipment, but anyway I know that a structure failed in a tremendous way, like what I show here, when the load to which the structure is subject is over the buckling limit, because after this the structure is unstable and cannot sustain the load anymore and start to collapse, and the collapse is what we need to crash our team. So the first things to do is a really simple analysis where we design our team. I give you the dimension. The radius is 40 millimeters, and the depth, because we extrude, is 80 millimeters. We assign a section, an homogeneous section, and the section is about 1 millimeters of thickness. We are going to use a very coarse mesh, not a refined one, using S4R element, so shell square element with the reduct integration. And the materials is common steel. This is the density expressed in kilogram on cubic millimeter. The elastic are Young modulus, Poisson ratio, and also the plastic behavior is modeled. In the linear analysis, so in the linear buckling load, the plastic behavior of our structure will not be taken into account. This is a really simple analysis. This is not capable to take into account nonlinearity like material, geometry, load, boundary condition. So there is not possibility to model, for example, a contact. This is just an analysis that we need to have a first number that we know the structure under this load will fail. As I told you in the other tutorial, we need to create a constraint, MPC constraint being with a control point here in the center and slave nodes here on the edge. This allows us to apply just one load and distribute this load perfectly to all the geometry. The load is this one, is applied here, and we put 1. One, because we didn't know the load, the buckling load. We want to know it. So the eigenvalue that the analysis will provide, multiplied for this, give us the first buckling load, expressed in Newton, obviously. I go very faster here because it's very similar to the other tutorial. And here I have the solution. Sorry. Results. This is the first eigenmode, and if I push forward, I cannot select other modes. Why? Because I impose to my model to just give me back the first mode for two reasons. The first, here, one. The first, because we just need the first buckling mode, because we just need the load that caused the instability of our structure. And the second is because we have a very coarse mesh, and if we try to achieve more than the first mode and the first eigenvalue, probably the solution will not be achievable due to the mesh. So I request just the first eigenvalue mode. And the results are here. And this number, the eigenvalue, this number is the load. So the load is 8.50 E05. So 850 kilonewton to produce not this contour. This is not the actual deformation. It's just the solution due to the eigenvalue, the eigenfunction used to solve the problem. But this number is the load. Is definitely the load that we need to cause the stability of our structure, and will be the first value of load that will be applied to the other simulation to produce a crash test, so, like this. To do this, we just copy. I prepare the complete model just to have a check of everything, but now I copy this model. I name him crash 2 just to do a step-by-step process. Okay, so we have the team. We need to create the crusher. So this create rigid shell planar with crusher 50 50 minus 50 minus 50. Okay. Now for a rigid I need a reference point, and I put 0 0 0, so in the center. I perform a mesh, selecting explicit, the type of mesh, structured. Okay, a very wide mesh. We don't need very refined. And then I have to apply a very important property, because without this the solver does not solve the problem. In this case it's not very important to assign a point mass and inertia. We refer to this one. We can put a mass expressed in this case in kilogram, because the density of our material is in kilogram, so every mass have be expressed in kilogram. We put just 1, and I calculated by hand the inertia for this dimension. And are kilogram for millimeter square. Oh, sorry. Okay. And this will not affect the solution at all, because we are not going to use something like gravity load, so the mass of the crusher is not very important. Obviously, it's important to know the mass of our object, because this will involve the energy, because this is going to move and will have a velocity. So the velocity is important because it create kinetic energy, and kinetic energy is obviously linked with the mass of the object. In this case, we are using a 1 kilogram crusher. So this is another parameter I think that you can model to see what's happened. And these are the rotatory inertia of your object, but as I show you, these are not really useful because we are going to oblige the plate, the crusher, to don't rotate to any axis. So these are pretty useless. But the system requires, so we need to put a value. In this case, I put a real value. Okay, so the crusher I think is complete. The thing have to be changed, just the mesh, because we have just to select a new mesh, the explicit, and always S4R. Okay, we save the model. The materials still okay. Okay, the assembly. Assembly have to be new because, or well, updated, because we have to put also the crusher. And okay, we are lucky, it put really near to the other object. But we have to move a bit, not a lot, but a bit, because he's still inside the object. So the start point is the reference point of the plate, and the new point is minus 0.25 millimeter. So in this direction, on the z axis. Okay, this is, I think, enough to avoid any problem and to don't introduce too much gap between the two objects, because this will be a problem for computational cost, because it's a time-dependent analysis. So the time that this plate move from the initial position to the position that actually touch the structure will be anyway calculated, and so will require time wasted. Okay, we can delete the attachment point because we no longer need this. It's just for the linear buckling analysis. The BC side is important because we need it. The load side no longer important. Okay, the RP1 very important. Surface, the first important part. Okay, crusher, surf. Okay, we have to select the crusher surface, and in this case it's very simple because we have just to click here. So purple is this side, we need the other one, the brown. So brown, but in some case many objects may cause a really many effort to select objects. So we can just click right on the thing and hide to just see the plate, and to show again, show. The same things we have to do for the cylinder. So thin external, we click on here, and then the external, so brown, and again mesh thin internal, purple. Okay, we save. So we created the set, the assembly is correct, the surface. Okay, we have to change the step, so we can just not delete, just replace with general and dynamic explicit. No linear geometry on. The time period is 1 second. We can put any number, and is linked to our problem. I know that 0.75 is a good time to achieve all the simulation, but you also can just put 1. Incrementation, mass scaling, and others are very important parameters. In this case and for this tutorial I will not touch these. I will leave them as they are, so as default. I just tell you that the incrementation is linked to the stability of your solution while the solver solve your problem and calculate the equation. The time scaling factor is a factor that allow you to decrease, in this case is 1. So he totally automatically calculate the stable increment, and so he decide the increment size, and this size can be scaled. For example, if you think that the simulation have to be more accurate, or you know that there are many problems of stability on your problem, you can scale. For example, 0.5 mean that your stable increment size will be scaled of 0.5. This what mean that you will need more time to accomplish your simulation, but obviously this will be more accurate. But depends by many things. For example, if your model is very ill-conditioned, what I mean, if you are going to excite some frequency of your structure with your load, in that case the structure start to vibrate. Vibration causes the increase of your kinetic energy, and this will bring you to a very no sense solution, or sometimes just to a never convergence solution. In this case we just put 1 because it's okay. The mass scaling is a very powerful technique, but that needs a very deep knowledge of your model and a bit experiences in this type of analysis. And numerically, what this tool do is just to modify the density of your materials model to boost the analysis. Obviously this is a numerical method, so you need to have some experimental, or anyway some data, some reliable data, then to compare your results with the reality, to be sure that your scaling does not affect the solution, so the reality. Last but not least, there are some damping factors that affect 2D element, linear bulk viscosity parameter, and quadratic bulk element, the 3D element. In this case I leave them default, but these parameters are like damping factor for problem that I mentioned before. For example, when your kinetic energy start to increase too much. These default parameters have to be always maintained as default, but depending on your problem, they may be changed, and they will affect obviously your results. I hope that this little explanation help you to understand what you need, but I don't expect that this help you a lot. It's just an introduction. Okay, we can rename this crash test. Okay, the field are okay. Interaction. So now we have to create the interaction. General contact, explicit. Okay. Select surface pair, and then crusher with external thin, crusher with internal thin, because we expect that the crusher may touch the external surface but also the internal one, and then thin external with internal. This make possible the simulation of every contact between every nodes of our model. Okay, then we have to create the contact property, contact, mechanical, tangential. We can select many type of contact. In this case, tangential behavior. We select frictionless. In some, for example, impact for ballet, may be useful to use the friction coefficient, but for this you need some experimental data. In this case, so we use frictionless. Okay, so we select this property. Okay, and we remove this one because in this case we doesn't use the load. The load, yes, we modify where is applied. Sorry, where it is applied. Sets, and we have to find this one, and now we put 150 kilonewton, so Newton, and the load in explicit analysis is better to not apply instantaneously, but with a smooth step on all time, because in this, or step time in this case is the same because we have just one step, step time 0 and 0. So this means that in the first incrementation we have no load, and 1 1. This means that he make a fifth order, if I don't remember, polynomial, something like this. Follow. I'm sorry, I have nothing to. Oops. Something like this, going from 0 to 1. So the load is applied with a smooth step, something like a heaviside step, but more smooth. Okay, so okay, then the boundary condition to the base, and also the boundary condition to the crusher, because we want that the crusher just go down, doesn't rotate or translate. So we constrain everything. This is because I say we doesn't need a lot the inertia, the real inertia, because we just avoid any rotation. Okay, is correct. I think that everything is okay. We can crash test. Okay, and okay, and I launch the simulation. Okay, sorry for this interruption. I just modified the field because the field was equal to 20 here. The envelope space-time intervals was 20. I put 100 because in this case we need more intervals to see more the effect of the analysis, and the results, if you submit the job, I already submit and terminate it because is very faster. The results is this one. And if you want just to see the effect of the compression do the action of the crusher, you can also remove this one and watch how the tin collapse. In this model there are no damage models, so you can also introduce such things inside the material definition. In this case we demonstrated that the buckling load applied to the tin with a constant load, obviously, will crush our tin. And obviously we can just lower down to do some tests until we see the more useful load that cause the complete crashing of your team. Obviously, lesser the load, more time pressure you need to crash all the team. I hope that you will enjoy this video, and I hope that this will be helpful for many of you. Thanks for watching. Bye.